Light does not stop instantly when it enters the ocean. It continues for a surprisingly long time, weakening molecule by molecule, meter by meter, until eventually there is nothing left of it. This is not a threshold you can point to. There is no line in the water where brightness becomes darkness. Instead, there is a slow gradient of decreasing energy, a place where photons arrive less and less frequently, until finally they stop arriving at all. Most of Earth's livable volume exists in this condition, not in darkness interrupted by light, but in darkness as the default state, where light is the anomaly that dissolved long ago. When sunlight meets the surface of the ocean, it does not simply pass through unchanged. Water is not transparent in the way air appears to be. It is a substance with density, with molecular structure, with the capacity to hold and scatter and absorb energy. Each photon that enters carries a specific wavelength, a particular frequency of electromagnetic oscillation, and the ocean responds differently to each one. Red light, with its longer wavelength, is absorbed almost immediately. Within the first 10 meters, the warmth of red fades into the surrounding water, converted into tiny increments of heat that disperse without trace. Orange follows soon after, then yellow. The ocean does not refuse this light dramatically. It simply takes it in, molecule by molecule, transforming visible brightness into invisible motion at the atomic scale. What remains travels deeper, but it is already diminished, already shifting toward the blue end of the spectrum. This is not a metaphor. The ocean literally becomes bluer as you descend, not because blue light is added, but because everything else has been removed. By 20 meters down, the reds and oranges are gone entirely. By 50 meters, even the greens have faded to near absence. What persists is a narrowing band of wavelengths, a spectrum that continues to collapse inward as depth increases. Blue light penetrates farthest because it scatters more readily, bouncing between water molecules in ways that allow it to travel longer distances before being absorbed. But scattering is not the same as preservation. Each bounce costs energy. Each interaction with a molecule, with a particle of suspended organic matter, with a dissolved ion, removes a small fraction of the photon's original intensity. The light that reaches 100 meters is not the same light that entered at the surface. It is quieter, colder, more diffuse. It arrives from all directions at once, no longer carrying the directionality of the sun. There are no shadows here. There is only a general omnidirectional glow that seems to come from the water itself. The rate of this fading is not constant. It depends on what the water contains. In the clearest parts of the open ocean, far from river outflow and coastal sediment, light can penetrate deeper than almost anywhere else on Earth. In these regions, the water is so pure, so free of particulate matter, that blue light can be detected by sensitive instruments at depths exceeding 200 meters. But detection is not the same as visibility. By 150 meters, the human eye would perceive only the faintest trace of illumination, a soft grayness without source or boundary. By 200 meters, even that is nearly gone. What remains is not enough to see by, not enough to cast even the suggestion of a shadow, but it is still measurable. Photons still arrive, just very rarely, separated by increasing intervals of time and space. The ocean's clarity varies. Near coastlines where rivers carry dissolved tannins and sediment, light is absorbed much more rapidly. In waters rich with phytoplankton, the greenness of chlorophyll shifts the spectrum, absorbing blue light and letting green penetrate slightly farther than it would in pure seawater. In these productive waters, the twilight zone begins earlier, perhaps at 50 meters instead of 100, but everywhere, regardless of local conditions, the same process unfolds. Light enters. Water absorbs it. Depth accumulates. Brightness fades. The transition is so gradual that it would be nearly impossible to notice if you descended slowly with it, watching the change happen in real time. There would be no moment when you could say, "Here, this is where it became dark." Instead, there would only be a continuous dimming, a slow withdrawal of the ability to distinguish form and color and distance, until finally the eyes find nothing left to interpret. The ocean has been divided into zones, layers defined by how much light penetrates them, but these divisions are human constructs imposed on a continuous gradient. The euphotic zone, the sunlit layer where photosynthesis can occur, extends from the surface to the depth where light intensity falls to 1% of its surface value. In the clearest ocean waters, this might reach 200 meters. In coastal waters, it might end at 30. Below this lies the dysphotic zone, the twilight region where light still arrives but too weakly to sustain photosynthetic life. And below that, the aphotic zone, where no sunlight penetrates at all. These names suggest boundaries, but the ocean does not recognize them. There is no barrier between twilight and darkness. There is only the ongoing reduction of photons, a steady decrease that continues without interruption, until it reaches a limit so profound that the concept of light becomes almost hypothetical. What we call the twilight zone, roughly from 200 meters to 1,000 meters in the open ocean, is not a place of dim illumination in the way a room at dusk might be. It is a realm where light arrives so infrequently that it cannot form a stable visual environment. A human eye, evolved to detect even faint sources of brightness, would find almost nothing to work with here. At 300 meters, the light level is approximately 1/10,000th of what exists at the surface. This is far below the threshold for human vision, below the level where rods and cones can generate meaningful signals. Yet it is not zero. Instruments can detect it. Certain organisms, with eyes far more sensitive than ours, can perceive it. But what they perceive is not a landscape, not a space with features and dimensions. It is only the faintest awareness that light exists somewhere above, a directional cue that points toward the surface without revealing anything about the surrounding water. The animals that live here have adapted to conditions where light is more concept than reality. Many have developed eyes of extraordinary sensitivity, with large lenses and retinas packed densely with photoreceptor cells, structures optimized to capture the smallest possible number of photons. Some species have eyes that point upward, designed solely to detect the silhouettes of prey or predators passing between them and the last traces of surface light. Others have abandoned visual reliance almost entirely, navigating instead through chemical gradients, pressure changes, vibrations in the water. Bioluminescence becomes more common as depth increases, not because the environment is darker in some new way, but because producing light begins to offer advantages that sunlight once provided. A flash of chemical luminescence can startle a predator, attract a mate, lure prey, or create confusion. But even this light is not constant. It appears in brief controlled bursts, and then the darkness returns unchanged. The physics of this region are difficult to contextualize in human terms. We are accustomed to darkness as the absence of light, as something that occurs when we close our eyes or turn off a lamp. But the darkness at 400 meters is not the same as the darkness of a closed room. It is not empty space waiting to be filled with illumination. It is water, dense and continuous, extending in all directions with physical properties that determine how energy moves through it. Light does not stop existing here because something blocks it. Light stops existing here because it has been methodically absorbed, photon by photon, across hundreds of meters of molecular interaction. Every oxygen atom, every hydrogen bond, every dissolved salt, every drifting particle has contributed to this outcome. The darkness is not an absence. It is a consequence, an endpoint reached through accumulated distance. By 600 meters, even the most sensitive instruments struggle to detect sunlight. What little arrives is indistinguishable from background noise, from the faint glow of radioactive decay in seawater, from the occasional photon produced by cosmic rays interacting with the upper atmosphere far above. The ocean here exists in a state that might be called functional darkness, a condition where the presence or absence of the sun makes almost no difference to the immediate environment. Yet this is still not the deepest darkness. Below this lies another 4,000 meters of water in the average ocean basin, regions where the concept of sunlight becomes entirely academic, where no photon from the surface has arrived in any measurable quantity for geologic spans of time. The transition into this deeper darkness is not abrupt. It is simply the final, quietest portion of a process that has been unfolding slowly since the first moment light entered the water. The volume of ocean water that exists in partial or complete darkness vastly exceeds the volume that receives adequate light for photosynthesis. If you were to calculate the total amount of seawater on Earth that lies below the euphotic zone, below the depth where plants can grow, it would account for more than 95% of the ocean's mass. This is not a thin layer of shadow beneath a bright surface. It is the dominant condition of the marine environment, the standard state of liquid water on this planet. The sunlit zone, despite its biological richness and its proximity to human experience, is an exception, a narrow band of illuminated fluid floating atop an enormously larger body of dark water. We tend to think of the ocean as a surface, as the boundary we see from shore or from ships, but the ocean is not its surface. The ocean is the entire volume beneath, the continuous mass of water extending downward for kilometers, and most of that mass has never been touched by direct sunlight in any form that would register as brightness. This inverts the intuitive understanding of light and dark. On land, darkness is what happens in the absence of the sun, a temporary condition that reverses with each dawn. In the ocean, darkness is the baseline. Light is the temporary visitor, growing weaker with every meter of depth until it is gone entirely, and what remains is a stability that does not change with the rotation of the Earth. At 1,000 meters, there is no day or night in the visual sense. The environment is as dark at noon as it is at midnight. Time, as marked by the passage of the sun, becomes irrelevant. What matters instead is depth, pressure, temperature, the slow drift of currents, the availability of food sinking from above. These are the variables that structure existence here, not the presence or absence of light. Human vision, even at its most sensitive, is designed for an environment rich in photons. The rod cells in the human retina, responsible for low-light vision, can theoretically detect a single photon under ideal laboratory conditions, but they require several photons arriving in quick succession to generate a conscious perception of light. In the deep twilight zone, photons arrive too infrequently and from too many scattered directions to form an image. The brain, receiving only sporadic signals, cannot construct a coherent visual field. There is nothing to focus on, no shape to distinguish from background, no sense of spatial orientation derived from sight. A human placed in this environment without artificial light would not see dimness, would not see shadows or vague forms. They would see nothing at all, a blackness as complete as if their eyes were closed, even though photons are still arriving, still interacting with the water around them, still carrying energy that could, under different circumstances, be interpreted as light. The animals that inhabit this region do not experience it the way we would. Many deep-sea fish have eyes so large relative to their body size that they seem almost absurd, spherical lenses occupying a significant portion of their skulls. These eyes are not built for detail or color. They are built to gather every available photon, to detect the faintest variation in an otherwise uniform field of near darkness. Some species have tubular eyes, fixed in place and aimed permanently upward, sacrificing peripheral vision for the ability to detect movement against the faint glow of the surface hundreds of meters above. Others have reflective layers behind their retinas, structures that bounce photons back through the photoreceptor cells a second time, effectively doubling their sensitivity. These adaptations suggest that even at depths where human vision fails completely, there is still information to be extracted from the environment, still meaning encoded in the rare arrival of light. But there is a point, somewhere between 800 and 1,000 meters depending on water clarity and time of day, where even these extraordinary eyes find nothing useful. The light that reaches this depth is no longer directional. It no longer indicates the location of the surface with enough precision to guide behavior. It becomes instead a kind of optical noise, indistinguishable from the faint bioluminescent glow of passing organisms, from the chemical reactions occurring in the water itself. Below this threshold, vision as a primary sense loses its utility. Eyes, if they persist, become reduced, simplified, or repurposed. Some deep-sea fish retain eyes, but use them only to detect bioluminescence, to see not the world, but the signals produced by other living things. Others abandon eyes entirely, navigating through touch, through electroreception, through lateral line systems that detect minute pressure changes in the water. The transition is not universal. There is no single depth where all light-dependent life disappears. But there is a region where the reliability of vision collapses, where the ocean ceases to be a place that can be meaningfully observed and becomes instead a place that must be sensed through other means. Below the depth where sunlight becomes undetectable, life does not disappear. It persists, but under conditions that require fundamental adjustments to the way energy is acquired and used. On the surface, energy enters the ocean as light, captured by phytoplankton and converted into chemical bonds through photosynthesis. This energy then moves through food webs, predator to prey, each transfer losing efficiency, each step up the chain representing a smaller fraction of the original solar input. But in the deep ocean, beyond the reach of photosynthesis, there is no local source of energy. The organisms here depend entirely on what falls from above, on the slow, continuous rain of organic material descending through the water column. Dead phytoplankton, fecal pellets, molted exoskeletons, fragments of larger animals, all of it drifts downward, pulled by gravity through increasingly cold and pressurized water. This descent is not rapid. A particle of marine snow, as this material is called, might take weeks to sink from the surface to the deep seafloor, tumbling slowly through currents, occasionally consumed by passing filter feeders, gradually decomposing as bacteria break down its organic components. By the time this material reaches 1,000 meters, much of its nutritional value has already been extracted. The largest, fastest sinking particles arrive first, dense aggregates of organic matter that plummet through the water column in a matter of days. The smaller, lighter fragments take longer, drifting in suspension, spreading laterally with currents, their descent more probabilistic than direct. What arrives at depth is not the rich, fresh detritus of the surface, but a diluted, degraded version, a kind of nutritional echo of the productivity occurring far above. Yet this is enough. The organisms that live here have evolved to function on remarkably little, to extract energy from sources that would seem negligible in a sunlit environment. Metabolism slows, growth rates decline, reproduction becomes less frequent. Life here operates at a pace that matches the scarcity of resources, a patient, methodical existence that can sustain itself on the minimum. The absence of light has secondary effects beyond the loss of photosynthesis. Temperature drops steadily with depth, not because light is warming the water directly, but because solar energy absorbed at the surface does not reach the deeper layers through convection or mixing at the same rate it is absorbed. By 1,000 meters, the water temperature in most of the ocean hovers just a few degrees above freezing, a cold that is constant and pervasive, unaffected by seasonal changes at the surface. This cold slows chemical reactions, reduces the metabolic rate of organisms, and increases the viscosity of water, making movement more energetically costly. At the same time, pressure increases by 1 atmosphere for every 10 meters of depth, reaching 100 atmospheres at 1,000 meters, a force sufficient to compress gas-filled spaces and alter the behavior of proteins. Yet life has adapted to these conditions as well, producing enzymes that function optimally under high pressure, maintaining cellular structures that do not collapse under stress, existing in equilibrium with an environment that would seem hostile from a surface perspective, but is simply the standard condition of the deep ocean. The combination of darkness, cold, and pressure creates a kind of biochemical stillness. Without the energetic input of sunlight, without the rapid temperature fluctuations that drive weather and mixing at the surface, the deep ocean is one of the most stable environments on Earth. Temperatures change by fractions of a degree over the course of centuries. Currents move slowly, measured in centimeters per second rather than meters. Seasonal variation, the cycle of bloom and decay that defines productivity in the euphotic zone, barely registers here. Instead, there is a steadiness, a uniformity that extends horizontally for thousands of kilometers and vertically for thousands of meters. This is not stagnation. Water still moves, nutrients still circulate, life still persists. But the pace is so reduced, so far removed from the rapid turnover of surface ecosystems, that time itself seems to operate differently. An organism here might live for decades, growing incrementally, reproducing rarely, waiting for the sporadic arrival of food from above. The ocean at this depth is patient in a way that has no terrestrial equivalent, a vast reservoir of cold, dark water where change occurs so slowly that it is nearly imperceptible. There is no horizon in the deep ocean. So on land, or on the surface of the sea, the horizon provides a reference point, a boundary between earth and sky, or water and air, that helps orient the body in space. Even in fog, or at night, there is usually some sense of distance, some gradient of visibility that extends outward before fading. But at depths where light no longer penetrates, there is no such gradient. Visibility is not reduced to a few meters or a few centimeters. It is reduced to nothing at all. The water in every direction is identical, equally dark, equally featureless. Without light to create contrast, without shadows to indicate form, the concept of distance becomes abstract. An object 1 meter away is indistinguishable from an object 100 meters away until it is touched, or until it produces its own light. The ocean here is not a space that can be surveyed or mapped through vision. It is an environment that must be navigated through memory, through instinct, through senses that do not depend on photons. Bioluminescence becomes the primary visual phenomenon in this realm, though it is sporadic and localized. The majority of deep-sea organisms are capable of producing light through chemical reactions, typically using luciferin compounds oxidized in the presence of oxygen and catalyzed by luciferase enzymes. The light produced is usually blue or blue-green, wavelengths that travel farthest in seawater, and are most easily detected by the eyes of deep-sea animals. But this light is not constant. It is generated only when needed, in brief flashes or sustained glows, and it serves specific purposes. Some fish use bioluminescent lures to attract prey, dangling light-producing organs in front of their mouths, waiting for smaller animals to investigate the glow. Others use light to communicate with potential mates, flashing species-specific patterns that can be recognized in the darkness. Still others employ bioluminescence as a defense mechanism, releasing clouds of glowing mucus or bacteria to confuse predators, or producing sudden bright flashes to startle attackers. Each use of light is deliberate, controlled, energetically expensive. Between these moments, the darkness returns, uninterrupted. The distribution of bioluminescence is not uniform throughout the ocean. It is most common in the twilight zone, between 200 and 1,000 meters, where the last traces of sunlight overlap with the first regions of true darkness. Here, many organisms still rely on detecting downwelling light from the surface and counter-illumination, the production of light on the ventral surface to match the faint glow from above, is a widespread camouflage strategy. A fish swimming below can look upward and see only silhouettes against the dim background brightness. By producing its own light on its underside, carefully matched in intensity and color to the ambient conditions, a predator or prey can effectively erase its silhouette, becoming invisible to observers looking up from below. This requires precise regulation. Too much light, and the organism becomes visible as a bright spot. Too little, and it casts a shadow. The control systems involved are remarkably sensitive, adjusting output in real time to match changes in ambient light levels as the sun moves across the sky far above. Below 1,000 meters, where no sunlight penetrates even in trace amounts, counter-illumination becomes irrelevant. There is no background light to match, no silhouettes to conceal. Bioluminescence here serves different functions, less about camouflage and more about communication, predation, and deterrence. The patterns become more diverse, the purposes more varied. Yet the fundamental nature of the environment does not change. Between the flashes, between the glows, there is only darkness, a stable, unchanging blackness that defines the space more thoroughly than any light ever could. The ocean at this depth is not lit by bioluminescence. It is occasionally interrupted by it, punctuated by brief moments of visibility that reveal nothing beyond their immediate vicinity and then vanish, leaving the darkness exactly as it was before. Sound moves through the deep ocean far more effectively than light ever could. While photons are absorbed within hundreds of meters, acoustic waves can travel for thousands of kilometers with relatively little attenuation. Water is an excellent conductor of sound, far better than air, and the cold, dense conditions of the deep ocean create acoustic channels where sound waves can propagate horizontally across entire ocean basins. This inversion of sensory priorities, where hearing becomes more informative than sight, defines the perceptual landscape of deep-sea organisms. What cannot be seen can often be heard, and the ocean that appears silent and empty to human intuition is, acoustically, surprisingly active. The speed of sound in seawater increases with pressure and decreases with temperature. In the deep ocean, these two factors create a zone of minimum sound velocity at roughly 1,000 meters depth, where cold water and moderate pressure combine to slow acoustic transmission. This layer acts as a waveguide, bending sound waves back toward it whenever they try to propagate upward or downward, trapping acoustic energy in a horizontal channel. Naval submarines have long exploited this feature, using the SOFAR channel, the sound fixing and ranging channel, to transmit signals across vast distances with minimal energy loss. But marine animals discovered this phenomenon millions of years before humans, and many species use low-frequency vocalizations that propagate through the SOFAR channel to communicate over distances that would be impossible through any visual means. Whales, for example, produce calls that can be detected thousands of kilometers away, their songs traveling through the deep sound channel and arriving at distant locations with enough clarity to convey information about identity, location, and reproductive status. The acoustic environment of the deep ocean is not chaotic. It is structured by physical laws that determine how sound propagates, reflects, and dissipates. High-frequency sounds, which carry more information but lose energy quickly, are used for short-range echolocation and communication. Dolphins and toothed whales use clicks in the tens of kilohertz range to map their immediate surroundings, bouncing sound waves off objects and interpreting the returning echoes with extraordinary precision. Deep-sea fish, some of which produce sounds through muscle contractions or gas bladder vibrations, use lower frequencies that travel farther but carry less spatial detail. The result is a layered acoustic space where different frequencies serve different functions, where organisms navigate and hunt and communicate through sound in ways that have no visual equivalent. The ocean is not silent. It simply speaks in frequencies and patterns that human ears, evolved for air, are not well adapted to perceive. Yet even sound has its limits. Acoustic communication requires energy, and in an environment where food is scarce, energetically expensive behaviors are minimized. Many deep-sea organisms are silent most of the time, producing sound only during specific activities like mating or territorial disputes. The ocean between these events is not empty of sound, but the sounds that persist are often passive. The incidental noise of water moving over surfaces, of bodies displacing fluid, of biological processes occurring without deliberate acoustic signaling. Some animals have evolved to listen for these passive sounds, to detect the presence of prey or predators through the faint vibrations they create in the water. The lateral line system, a series of sensory organs running along the sides of fish, detects pressure changes and low-frequency vibrations with remarkable sensitivity, allowing the animal to perceive movement and proximity without needing to produce or hear sound actively. This is a kind of acoustic touch, a way of feeling the water's motion and interpreting it as information about the surrounding environment. The darkness of the deep ocean, then, is not a sensory void. It is an environment where different modalities replace vision, where sound and pressure and chemical gradients provide the information that light would offer in shallower waters. The absence of photons does not make the environment unknowable. It simply requires that knowledge be constructed through other means, through senses that operate independently of electromagnetic radiation, through adaptations that have been refined over hundreds of millions of years of evolution in darkness. Pressure in the deep ocean increases at a rate that is perfectly predictable and perfectly relentless. Every 10 meters of depth adds approximately 1 atmosphere of pressure, the equivalent of the entire weight of Earth's atmosphere at sea level, stacked again and again in increments that accumulate without variation. By 1,000 meters, the pressure is 100 times greater than at the surface. By 4,000 meters, The average depth of the ocean floor, it is 400 atmospheres. This is not a force that can be felt in the way surface-dwelling organisms feel wind or current. It is a constant, omnidirectional compression that acts on every molecule simultaneously, squeezing water into a denser configuration, reducing the volume of any gas-filled space, altering the physical properties of substances in ways that become significant only when measured with precision instruments. Water itself is nearly incompressible, which is why pressure increases so uniformly with depth. Gases, by contrast, compress readily. A balloon filled with air at the surface would shrink to a tiny fraction of its original volume if carried to the deep sea floor, the gas molecules forced closer together by the surrounding pressure. Organisms that rely on gas-filled structures for buoyancy, such as certain fish with swim bladders, cannot survive at extreme depths without significant modification. The swim bladder, an internal organ that fish use to maintain neutral buoyancy by adjusting the volume of gas it contains, becomes a liability in deep water. The pressure would collapse it, or the energy required to maintain gas volume against compression would become prohibitively expensive. Deep-sea fish have evolved alternative strategies. Many have reduced or eliminated their swim bladders entirely, relying instead on lipid deposits, which are less dense than water but incompressible, to achieve near-neutral buoyancy. Others have given up on buoyancy altogether, becoming negatively buoyant and living on or near the seafloor where sinking is not a disadvantage. Proteins, the molecular machines that perform nearly all biological functions, are sensitive to pressure. At high pressures, the three-dimensional shapes that proteins fold into can become unstable, disrupting their ability to catalyze reactions or bind to other molecules. Deep-sea organisms produce specialized proteins, often containing different amino acid sequences than their shallow water relatives, that maintain functionality under compression. These are not dramatically different proteins. The changes are subtle, minor adjustments in structure that allow the molecule to resist deformation. But they are essential. A shallow water fish brought to the deep ocean would find its enzymes malfunctioning, its cellular processes slowing or stopping as proteins lost their proper configuration. Conversely, a deep-sea fish brought to the surface experiences the opposite problem. The reduction in pressure causes proteins optimized for high-pressure conditions to become unstable, to unfold or aggregate, leading to cellular dysfunction. The pressure at which an organism lives is not merely an environmental parameter. It is a constraint that shapes biochemistry at the molecular level. The uniformity of pressure at any given depth contributes to the stability of the deep ocean environment. Unlike temperature, which varies with latitude and season, or salinity, which changes with proximity to freshwater sources, pressure is determined solely by depth. An organism at 3,000 meters in the Pacific experiences the same pressure as an organism at 3,000 meters in the Atlantic, the same pressure as an organism at 3,000 meters anywhere on Earth. This consistency creates ecological conditions that are more geographically uniform than almost any terrestrial environment. The deep ocean does not have climatic zones in the traditional sense. It has depth zones, and within each depth zone, conditions are remarkably similar regardless of location. This allows deep-sea species to have extraordinarily wide geographic ranges, distributions that span entire ocean basins, because the environment they are adapted to exists continuously across vast horizontal distances. A species found off the coast of California might also be found in the mid-Atlantic ridge, thousands of kilometers away, because the deep sea floor at similar depths offers essentially identical physical conditions. The cold, the darkness, and the pressure together create an environment where time seems to operate at a different scale. Biological processes slow. Growth rates measured in millimeters per year are common. Some deep-sea fish live for decades, reaching sexual maturity only after 10 or 15 years. Coral-like organisms in the deep sea, such as certain bamboo corals, grow so slowly that individual colonies can be centuries old, their oldest sections formed before the Industrial Revolution, their structure recording environmental changes across spans of time that exceed human lifetimes. The ocean here is ancient, not just in the geological sense, but in the biological sense. a place where individual lives extend across durations that make the rapid turnover of surface ecosystems seem almost frantic. The seafloor in the deepest parts of the ocean is not a dramatic landscape. There are no towering mountains in most places, no sudden cliffs or valleys, no features that would register as landmarks in a terrestrial sense. Instead, there are abyssal plains, vast stretches of nearly flat terrain that extend for thousands of kilometers in every direction, interrupted only occasionally by isolated seamounts or the gentle undulations of buried tectonic features. These plains are among the flattest surfaces on Earth, their gradients so slight that they would be imperceptible to a human walking across them, their topography measured in meters of elevation change over distances of tens of kilometers. They are covered by sediment, a fine layer of material that has been accumulating for millions of years, settling grain by grain through the water column, building up at rates so slow that a single centimeter of thickness might represent thousands of years of deposition. This sediment is not uniform. It is composed of multiple sources, each contributing different components to the mixture. Terrigenous sediment, material eroded from continents and carried by rivers into the ocean, settles out in coastal regions and rarely reaches the deep abyssal plains unless transported by turbidity currents or submarine landslides. Biogenic sediment, the remains of organisms that lived in the sunlit surface waters, makes up a larger fraction of deep-sea deposits. The shells of planktonic foraminifera, the tests of radiolarians, the frustules of diatoms, all of these microscopic structures sink after the organisms die, their calcium carbonate or silica skeletons accumulating on the seafloor in layers that record the productivity of the surface ocean over geologic time. In some regions, these biogenic oozes are meters thick, representing millions of years of continuous deposition. In other regions, particularly at the greatest depths, even biogenic material dissolves before it reaches the bottom. As the pressure increases the solubility of calcium carbonate and silica, leaving only red clay, a fine-grained residue of wind-blown dust, volcanic ash, and the occasional meteorite fragment. The rate of sediment accumulation is extraordinarily slow. On the abyssal plains, away from continental margins and areas of high biological productivity, sediment might accumulate at a rate of 1 millimeter per 1,000 years. This is not a rate that can be observed. It is a rate that must be inferred from measurements, from the dating of sediment cores, from the counting of layers that represent ice ages and interglacial periods, volcanic eruptions, and meteor impacts. The surface of the seafloor, the layer currently in contact with the bottom water, is not new. It is not fresh. It is a surface that has been exposed for centuries, accumulating material so gradually that the distinction between present and past becomes almost meaningless. A grain of sediment that settled 1,000 years ago lies only a millimeter below the surface, still within the bioturbated zone where bottom-dwelling organisms occasionally disturb the sediment, mixing layers together, erasing fine-scale temporal resolution. Life on the abyssal plains exists at densities far lower than anywhere in the sunlit ocean. A square meter of seafloor might contain a few small crustaceans, a brittle star, a sea cucumber, a scattering of bacteria in the sediment. These organisms are spread so thinly across the landscape that they rarely encounter one another. The energy available to support them comes almost entirely from the rain of organic material from above, and in the deep central ocean basins, this rain is sparse. Most of the organic matter produced at the surface is consumed or decomposed long before it reaches the abyssal seafloor. What arrives is highly degraded, low in nutritional value, distributed unevenly in space and time. Occasionally, larger food falls arrive, the carcass of a whale or a large fish sinking rapidly through the water column and coming to rest on the bottom. These events are rare, but when they occur, they create localized oases of abundance, attracting scavengers from across the surrounding area, supporting entire communities that persist until the carcass is completely consumed. Between these events, the seafloor returns to its baseline state, a vast, nearly featureless plain where life persists at the absolute minimum density that can sustain reproduction. Humans have visited the deepest parts of the ocean, but only briefly, encased in vessels designed to withstand pressures that would instantly crush unprotected tissue. The first successful descent to the Challenger Deep, the lowest point in the Mariana Trench, occurred in 1960, when the bathyscaphe Trieste carried 2 men nearly 11 kilometers below the surface. The journey took hours, a slow descent through darkness that deepened with every meter, the hull creaking under compression as external pressure mounted. At the bottom, the explorers saw a flat, featureless plain through a small viewport, illuminated only by the artificial lights of the vessel. They stayed for 20 minutes before releasing ballast and beginning the equally slow ascent back toward the surface. Since then, only a handful of crewed expeditions have returned to similar depths, and even with modern technology, the experience remains fundamentally constrained by the limits of human physiology and engineering. We cannot exist in the deep ocean as we exist on land or at the surface. We can only visit it briefly, as observers contained within protective shells, pressing our faces against thick acrylic windows and watching a world that exists independently of our presence. The submersibles used for deep-sea exploration are not large. Most accommodate only 2 or 3 people, seated in a titanium or steel sphere barely 2 meters in diameter, surrounded by instruments, life support systems, and batteries. The walls of these spheres are thick, engineered to resist the immense external pressure, and they leave little room for movement. The experience of descent is claustrophobic by necessity, a slow journey through absolute darkness punctuated only by the glow of instrument panels and the occasional glimpse of bioluminescent organisms drifting past the viewport. Communication with the surface is limited to acoustic signals, sound waves transmitted through the water at intervals, providing updates on depth, position, and status. There are no windows in the traditional sense, no panoramic views, only small reinforced ports that offer a restricted field of vision. The ocean beyond is invisible until the submersible's lights are activated, and even then, the illumination extends only a few meters into the surrounding water before being absorbed entirely. The environment revealed is always partial, always fragmentary, a small bubble of visibility surrounded by infinite blackness. What these expeditions have documented is an environment that remains largely unchanged by human activity. The deep sea floor, far removed from the surface and its industrial processes, does not show the same signs of degradation visible in coastal ecosystems or even mid-depth waters. There is no plastic here from decades ago, though recent surveys have begun to detect microplastic particles even at the greatest depths, evidence that human influence now reaches into regions once considered entirely remote. But the overall structure of the deep-sea ecosystem, its composition and function, appears stable, operating on timescales so long that human observation spans only the briefest fraction of its history. Their submersible might visit a particular site once every few years, and between those visits, the seafloor remains in darkness, undisturbed except by the slow processes of sedimentation and the occasional passage of deep-sea organisms. The presence of a submersible is an anomaly, a momentary intrusion of light and noise into an environment where neither belongs. The technology required to reach these depths is expensive and complex, which means that the majority of the deep ocean remains unexplored. More people have walked on the surface of the moon than have descended to the deepest parts of the ocean. The total area of seafloor that has been directly observed by human eyes or cameras is a minuscule fraction of the total area available, perhaps less than 1%. The rest is known only through indirect measurements, through sonar mapping that provides topographic data without visual confirmation, through sediment cores that sample the composition of the bottom without revealing what lies there. The deep ocean is not unknown in the sense that it is completely mysterious, but it is largely unobserved, a vast region that exists in a state of near-total isolation from human experience, its details inferred rather than documented, its daily reality unwitnessed. The deep ocean operates on timescales that are difficult to reconcile with human perception of time. On land, or even at the ocean's surface, change is frequent and observable. Seasons shift, storms pass, organisms grow and die within spans that can be witnessed directly. But in the deep ocean, the relevant timescales stretch far beyond the duration of individual human lives, beyond the duration of human civilizations, into geologic and evolutionary time. A deep-sea coral colony growing at a rate of 1 centimeter per decade will take a century to add 10 centimeters to its height. A sediment layer accumulating at 1 millimeter per thousand years will add only 1 meter of thickness over 1,000,000 years. These are not rates that can be experienced. They can only be calculated, extrapolated from measurements taken at intervals, separated by years or decades, projected backward and forward through time using assumptions about constancy and uniformity. This temporal slowness is not a deficiency. It is a fundamental characteristic of an environment where energy is scarce and metabolic rates are low. In the absence of abundant food, organisms cannot afford rapid growth or frequent reproduction. Every biological process that requires energy must be rationed, prioritized, stretched across longer durations than would be necessary in a more productive habitat. The result is a kind of biological patience, an existence structured around waiting, around enduring long periods of inactivity punctuated by brief opportunities for feeding or reproduction. A deep-sea fish might go weeks without encountering prey, its metabolism slowed to conserve energy, its body drawing on stored lipids to maintain essential functions. When food does arrive, the response is immediate but measured. The energy gained allocated carefully across the various demands of survival. There is no surplus here, no excess that allows for experimentation or rapid adaptation. Life in the deep ocean is efficient by necessity, operating at the minimum viable level, persisting rather than thriving. The isolation of the deep ocean from surface processes also contributes to its temporal disconnection. Events that dominate the upper ocean, such as seasonal plankton blooms or storm-driven mixing, have only muted effects at depth. The rain of organic material from the surface varies slightly with season, more abundant in spring and summer when surface productivity is high, less abundant in winter when photosynthesis slows. But by the time this material reaches the abyssal sea floor, the seasonal signal is so attenuated, so spread out in time by the slow descent through thousands of meters of water, that it becomes almost undetectable. The deep seafloor experiences a kind of temporal smoothing, where rapid surface fluctuations are averaged out, leaving only the slowest, longest-term trends. Climate shifts that unfold over centuries or millennia, changes in ocean circulation driven by tectonic activity or ice age cycles, these are the variations that matter at depth. The daily and seasonal rhythms that structure life in the sunlit zone are irrelevant here. This does not mean the deep ocean is static. It changes, but the changes occur so slowly that they are invisible on human timescales. The position of a tectonic plate shifts by centimeters per year, but over millions of years, this movement opens new ocean basins, closes old ones, builds seamounts and ridges that alter current patterns and sediment distribution. The composition of the water itself changes as climate cycles progress, as ice sheets grow and shrink, as the balance between evaporation and precipitation shifts. These changes affect deep-sea organisms, driving evolution, extinction, adaptation, but they unfold across so many generations that no individual organism experiences them as change. Instead, each generation inherits an environment that is effectively identical to the one its ancestors inhabited, and the slow drift of conditions over deep time is recorded only in the fossil record, in the shifting compositions of sediment layers, in the genetic differences that accumulate between populations separated by geographic or temporal distance. There is something profoundly calming in this slowness, in the recognition that the deep ocean exists in a state largely unaffected by the rapid fluctuations that dominate human experience. The concerns that structure daily life on land, the urgencies and deadlines, the seasonal preparations and responses, none of these have meaning in an environment where a year passes without noticeable change, where a human lifetime is a brief flicker in a continuum that extends across millions of years. The deep ocean is not aware of this, of course. It does not experience its own slowness as slowness because there is no faster reference point against which to measure it. It simply exists, operating according to the physical and biological constraints that define it, indifferent to the pace of the world above. The majority of life in the deep ocean is not visible to the human eye, even when illuminated. Bacteria and archaea, single-celled organisms that exist in densities orders of magnitude greater than any multicellular life, dominate the biomass of the deep seafloor and the water column above it. These microorganisms are not dramatic. They do not move in ways that register as motion. They do not glow or emit sounds. They simply exist, metabolizing slowly, dividing infrequently, performing chemical transformations that are essential to the functioning of the entire ocean system, but which occur at molecular scales too small to observe directly. A single gram of deep-sea sediment might contain millions or billions of bacterial cells, packed between sediment grains, existing in conditions where oxygen is scarce or absent, where temperature hovers just above freezing, where pressure compresses every cellular structure. Yet they persist, and in persisting they mediate processes that connect the deep ocean to the global cycles of carbon, nitrogen, sulfur, and other elements. The metabolic strategies available to deep-sea microorganisms are diverse, reflecting the varied chemical environments they inhabit. In oxygenated bottom waters, aerobic bacteria decompose organic matter, breaking down complex molecules into simpler compounds and releasing carbon dioxide in the process. This decomposition is slow, constrained by the low temperatures and limited availability of nutrients, but it is continuous, occurring across the entire seafloor wherever organic material accumulates. Below the sediment surface, where oxygen penetrates only a few millimeters or centimeters before being consumed, anaerobic bacteria take over, using alternative electron acceptors such as nitrate, sulfate, or even iron and manganese oxides to extract energy from organic compounds. These pathways are less efficient than aerobic respiration, yielding less energy per molecule metabolized, but they allow life to persist in environments where oxygen is unavailable. The result is a stratified microbial ecosystem within the sediment, with different metabolic guilds occupying different chemical niches, each adapted to the specific conditions present at their depth within the sediment column. Chemosynthesis, the use of inorganic chemical reactions as an energy source rather than sunlight, occurs throughout the deep ocean but is most concentrated at hydrothermal vents and cold seeps, locations where chemical disequilibria between seawater and the underlying crust create opportunities for energy extraction. At hydrothermal vents, superheated water rich in hydrogen sulfide, methane, and other reduced compounds erupts from the seafloor, mixing with cold, oxygenated seawater. Bacteria that can oxidize these compounds, converting hydrogen sulfide to sulfate or methane to carbon dioxide, gain energy in the process, energy that can be used to fix carbon from dissolved carbon dioxide into organic molecules. These chemosynthetic bacteria form the base of vent ecosystems, supporting dense communities of animals such as tube worms, mussels, and crabs that either harbor the bacteria as symbionts or graze on bacterial mats growing on rock surfaces. The productivity of these systems, measured in grams of carbon fixed per square meter per year, can rival or exceed that of sunlit surface waters, a remarkable inversion of the usual energy hierarchy where life at depth depends entirely on resources descending from above. But hydrothermal vents and cold seeps are exceptions, localized anomalies in an otherwise energy-poor environment. The vast majority of the deep seafloor is far from any vent system, and the microbial communities there must subsist on the sparse organic matter that rains down from the surface or on chemical gradients so subtle that only the most efficient metabolic pathways can exploit them. In some regions of the deep ocean, particularly beneath the least productive surface waters, the flux of organic material to the seafloor is so low that microbial activity in the sediment is barely detectable. Cells in these sediments may divide only once every few decades or centuries, spending most of their existence in a state of near dormancy, their metabolic rates reduced to the absolute minimum required to maintain cellular integrity. Yet they remain viable, capable of responding to the occasional arrival of food or the slow migration of chemical gradients through the sediment. This is life operating at the edge of thermodynamic feasibility, extracting energy from sources so dilute that the boundary between living and non-living becomes difficult to define. The chemical transformations mediated by these microorganisms are not isolated events. They are part of global biogeochemical cycles that link the deep ocean to the atmosphere, to the land, to the sunlit surface waters. Carbon that is fixed by photosynthesis at the surface eventually sinks to depth, where it is either buried in sediments, sequestered for millions of years until tectonic processes return it to the surface, or decomposed by bacteria and return to the water column as dissolved carbon dioxide. Nitrogen, fixed from atmospheric nitrogen gas by surface-dwelling cyanobacteria, cycles through the ocean in various forms, some of which are converted back to nitrogen gas by denitrifying bacteria in oxygen-depleted sediments. Sulfur, weathered from rocks on land and carried to the ocean by rivers, is reduced to sulfide by bacteria in anaerobic sediments and then reoxidized when sediments are mixed or when the sulfide diffuses into oxygenated waters. These cycles operate continuously, connecting every part of the ocean to every other part, linking the deep seafloor to processes occurring thousands of kilometers away and thousands of meters above. The water in the deep ocean is not stagnant. It moves, but at velocities so slow that the concept of current becomes almost abstract. Deep water circulation is driven primarily by differences in density, which in turn are determined by temperature and salinity. At high latitudes where surface water is cooled by contact with polar air and made more saline by sea ice formation, dense water sinks, descending through the water column until it reaches a depth where its density matches that of the surrounding water. This water then spreads horizontally, flowing along surfaces of constant density, moving away from the regions where it formed and into the global ocean interior. The process is called thermohaline circulation, and it operates on timescales of centuries to millennia. A parcel of water that sinks in the North Atlantic might not return to the surface until it has traveled through the entire deep ocean, passing through the South Atlantic, around Antarctica into the Indian and Pacific basins, gradually mixing with surrounding water, slowly warming and losing its distinct chemical signature. The speed of this circulation is measured in millimeters per second in most places, slow enough that a drifting particle would take years to travel distances that surface currents could cover in weeks. Yet this slow movement is sufficient to transport dissolved oxygen, nutrients, and heat throughout the deep ocean, preventing it from becoming a completely isolated reservoir. Without this circulation, the deep ocean would eventually become anoxic, depleted of oxygen as bacteria and other organisms consumed what was available and no mechanism existed to replenish it. But the continual gradual inflow of cold, oxygen-rich water from polar regions maintains oxygenated conditions even at the greatest depths, allowing aerobic life to persist in environments that would otherwise be chemically inhospitable. The circulation also transports nutrients released by decomposition in the deep ocean back toward the surface, where upwelling brings them into contact with sunlight and allows them to support new photosynthesis. This vertical exchange, though slow, is essential to the productivity of the entire ocean system. The water masses that make up the deep ocean can be distinguished by their temperature, salinity, and dissolved gas concentrations, properties that reflect their origins and the time since they were last at the surface. Antarctic bottom water, formed around the Antarctic continent, is the densest and coldest water in the ocean, spreading along the seafloor and filling the deepest basins. North Atlantic deep water, formed in the Norwegian and Labrador seas, is slightly warmer and less dense, occupying intermediate depths in the Atlantic and spreading into other basins at mid-depth levels. These water masses do not mix rapidly. They slide past one another, layered by density, their boundaries marked by gradual changes in temperature and salinity rather than sharp transitions. A vertical profile of the ocean, measured from surface to seafloor, reveals this stratification with warmer, lighter water near the surface and colder, denser water at depth, the transition occurring smoothly across hundreds or thousands of meters. The isolation implied by this stratification is real but not absolute. Water masses do eventually mix, though the process is slow, and primarily occurs at boundaries where turbulence is enhanced by interaction with topography or by internal waves propagating through the ocean interior. A seamount rising from the abyssal plain can deflect deep currents, creating eddies and turbulent mixing that transfers properties between adjacent water masses. Internal tides, generated when barotropic tides flow over underwater ridges, propagate energy into the deep ocean and dissipate through small-scale turbulence that mixes water vertically. These processes are diffuse, distributed across the entire ocean, and individually weak, but collectively they are sufficient to prevent the deep ocean from becoming completely stratified and stagnant. The result is a balance between the slow overturning circulation that renews deep water and the equally slow mixing that homogenizes it, a balance that has been maintained, with variations, for millions of years. The deep ocean's role in regulating Earth's climate is substantial, but operates on timescales that are difficult to perceive directly. The ocean stores more heat than the atmosphere by several orders of magnitude, and the deep ocean, because of its immense volume, holds the majority of that stored heat. Changes in the rate of deep water formation, driven by shifts in polar temperatures or ice cover, can alter the distribution of heat within the ocean and affect the exchange of heat between ocean and atmosphere. Similarly, the ocean absorbs carbon dioxide from the atmosphere, and much of that carbon is eventually transported to depth through the sinking of organic material and the downwelling of carbon-rich water. The deep ocean thus acts as a reservoir for carbon, sequestering it on timescales of hundreds to thousands of years, removing it from the atmosphere where it would otherwise contribute to warming. These processes do not operate in isolation. They are part of a coupled system where changes in one component, such as atmospheric carbon dioxide concentration or ocean temperature, propagate through feedbacks that affect circulation, productivity, and the distribution of chemical species throughout the ocean. There is a fundamental difficulty in describing the deep ocean to someone who has never been there, and perhaps an even greater difficulty in describing it to someone who has. The experience of descending in a submersible, of sitting in a cramped sphere surrounded by instruments and watching the water outside the viewport grow darker and darker until even the most powerful lights reveal only a few meters of empty blackness, is so removed from ordinary sensory experience that language struggles to convey it. The darkness is not like closing your eyes. The silence is not like a quiet room. The pressure, though not felt directly inside the protective hull, is present as an awareness, a knowledge that the water outside is exerting forces sufficient to compress steel, to collapse structures, to render the human body instantly non-viable. Yet the submersible does not feel like a place under siege. It feels stable, contained, separate from the environment in a way that makes the external conditions seem almost theoretical. The ocean beyond the viewport could be water, or it could be some other substance entirely. There is no way to verify except through instruments, through temperature sensors and pressure gauges, through sonar readings that translate acoustic reflections into distance measurements. What the instruments reveal is an environment that is remarkably uniform over large spatial scales, but contains localized variations that can only be detected through direct observation. A camera lowered on a tether from a surface ship might capture images of the seafloor at regular intervals, providing snapshots of bottom topography and fauna, but it cannot convey the continuity of the environment, the sense that this particular patch of seafloor is part of an unbroken plain extending in all directions for hundreds of kilometers. A sediment core brought up from depth provides detailed information about the composition and layering of the bottom, but it is only a vertical slice, a one-dimensional sample of a three-dimensional space, and the inferences drawn from it depend on assumptions about lateral uniformity that may or may not be valid. The deep ocean is known through fragments, through isolated measurements that are then extrapolated, interpolated, and stitched together into models that approximate reality but cannot capture it fully. The organisms that live in the deep ocean are known in a similarly fragmented way. Many species have been observed only a handful of times, collected by trawls or documented by remotely operated vehicles during brief transects across the seafloor. Their behavior, their life cycles, their ecological interactions are inferred from limited data, from the examination of preserved specimens, from fleeting video recordings that show them in contexts that may not be representative of their typical existence. A fish captured in a trawl net arrives at the surface dead or dying, its body decompressed, its tissues damaged by the rapid change in pressure, its colors faded by the absence of the chemical gradients that maintained them in life. What can be learned from such a specimen is constrained by the violence of its collection. Its anatomy can be described, its stomach contents analyzed, its genetic material sequenced, but its behavior, its response to its environment, the way it moved through the water and interacted with other organisms, all of this is lost. The deep ocean, as experienced by the organisms that live there, remains largely inaccessible to direct human observation. This inaccessibility is not merely a technical challenge that might be overcome with better instruments or more funding. It is, in part, a consequence of the fundamental differences between human sensory systems and those of deep-sea organisms. We are visual creatures, reliant on light to navigate and interpret our surroundings, and the absence of light in the deep ocean renders much of our primary sensory modality useless. We can bring artificial light, and we do, but in doing so we alter the environment we are trying to observe. Organisms that have never encountered bright light in their evolutionary history may respond to it in ways that are not representative of their normal behavior. They may be attracted to it, repelled by it, disoriented by it. The presence of a submersible with lights is not a neutral observation. It is an intervention, a disturbance that changes the system being studied. What is seen in the light of a submersible is not the deep ocean as it exists in darkness. It is the deep ocean responding to the presence of light, a fundamentally different condition. The deep ocean exists whether or not it is observed, and it has existed in more or less its current form for tens of millions of years, far longer than humans have been present on Earth, far longer than most of the species currently living in it. This continuity, this persistence across geological time, places the deep ocean in a category of environments that are fundamentally independent of human experience. We did not discover it in the sense that we discovered new lands or new species. We became aware of it gradually, through instruments and indirect measurements, through the slow accumulation of data that revealed the existence of a vast volume of water existing in permanent darkness beneath the surface we sailed across. But the deep ocean was not waiting to be discovered. It was simply there, functioning according to physical and biological principles that operated long before we existed and will continue to operate long after. The spatial scale of the deep ocean is difficult to internalize. The average depth of the ocean is approximately 3,700 meters, and the total volume of seawater on Earth is roughly 1.335 billion cubic kilometers. Of this volume, only a tiny fraction receives enough light for photosynthesis, perhaps the upper 200 meters in the clearest waters, often much less. The remaining volume, the dark water below the euphotic zone, represents more than 95% of the total livable space on Earth, more than all terrestrial habitats combined, more than all freshwater lakes and rivers, more than the entire atmosphere. This is not a marginal environment. It is the dominant environment, the standard condition of liquid water on this planet, and yet it is the environment humans are least equipped to inhabit or even observe directly. We are surface creatures, adapted to air and light, to temperatures and pressures that exist only in the thinnest possible layer of the Earth's fluid envelope. The deep ocean, by contrast, is adapted to conditions that are hostile to us, conditions that require significant technological mediation even to briefly visit. This inversion of perspective, the realization that what we consider normal is actually exceptional, and what we consider extreme is actually typical, has implications that extend beyond marine biology or oceanography. It suggests that our understanding of life, of habitability, of what constitutes a viable environment, is shaped by the narrow range of conditions we personally experience. We think of darkness as the absence of light, as something unusual or temporary, because we live in an environment where light is abundant for half of each day. But in the ocean, darkness is the default, and light is the temporary intrusion, present only in the uppermost layer and fading quickly with depth. We think of pressure as something that must be contained or resisted, because we live at the bottom of a relatively thin atmosphere where pressure variations are small. But in the ocean, pressure increases continuously with depth, and organisms at the seafloor experience pressures hundreds of times greater than what we consider normal without requiring any protective barrier. The deep ocean does not accommodate human physiology. it is indifferent to it. It simply is, and life there has adapted to conditions that we find incomprehensible. The silence of the deep ocean, the stillness, the lack of rapid change, these qualities create an environment that feels, from a human perspective, almost timeless. There is no sunrise or sunset, no seasons in the visual sense, no daily cycle of temperature or light that marks the passage of time. An organism at 3,000 meters depth exists in conditions that are effectively identical from one day to the next, from 1 month to the next, from 1 year to the next. Change occurs, but it occurs so slowly that it would be imperceptible within the lifetime of any individual observer. This constancy, this stability, is so unlike the dynamic, rapidly changing environments where humans evolved that it challenges our intuitive sense of what an environment should be. We are accustomed to variety, to fluctuation, to conditions that change hourly or daily. The deep ocean offers none of this. It offers only continuity, a sameness that extends across vast distances and long periods, broken only by rare events that are themselves absorbed back into the prevailing stillness. Light stops gradually, molecule by molecule, photon by photon, until there is simply nothing left of it to measure. The transition is so smooth that it would be impossible to identify the exact moment when seeing becomes impossible, when the last faint trace of surface brightness finally dissolves into the surrounding darkness. This is not a threshold that announces itself. It is a continuum that extends across hundreds of meters, a gradient so gentle that it feels less like crossing a boundary and more like settling into a condition that was always present, waiting beneath the brief interruption of illumination. The deep ocean does not require light to function. It does not depend on visibility or color or the daily cycle of brightness and shadow. It operates according to principles that are independent of electromagnetic radiation, that rely instead on pressure, temperature, chemistry, the slow drift of currents, the patient accumulation of sediment, the quiet metabolism of organisms adapted to scarcity. Life here does not struggle against the darkness. It simply exists within it, as it has for hundreds of millions of years, as it will continue to exist for as long as liquid water remains on Earth and gravity continues to pull organic matter downward through the water column. There is something calming in the recognition that this environment does not change in response to human awareness of it. The deep ocean was dark before we knew it existed, and it remains dark whether or not we direct our attention toward it. It is governed by physical laws that operate continuously, indifferently, without need for observation or interpretation. The pressure at 4,000 meters is the same whether measured by an instrument or left unmeasured. The temperature hovers near freezing whether recorded or ignored. The sediment accumulates at rates determined by the productivity of surface waters and the efficiency of bacterial decomposition, processes that unfold according to their own internal logic, unaffected by the presence or absence of human observers. Most of Earth's water exists in this state. Most of the ocean's volume lies below the depth where light penetrates, below the narrow band of illuminated water that we think of when we imagine the sea. The darkness is not an exception. It is the rule, the baseline condition, the environment that defines the majority of the marine world. And within this darkness there is stability, continuity, a kind of biochemical patience that has no equivalent in the sunlit surface. Time moves differently here, or perhaps it simply becomes less relevant, less tied to the rotation of the Earth and the passage of the sun, more aligned with the slow drift of deep water masses, the gradual compaction of sediment, the unhurried lives of organisms that grow by millimeters per year and reproduce once or twice in a lifetime that spans decades. The deep ocean does not need to be understood to exist. It persists whether or not we map its topography, sample its water, catalogue its organisms. It is complete in itself, a system that functions according to principles we are still learning, perhaps principles we will never fully comprehend, not because they are hidden, but because they operate on scales and timescales so removed from human experience that our intuitions fail us. And perhaps this is enough. Perhaps the deep ocean can remain mostly unknown, mostly unobserved, a vast reservoir of cold, dark water that reminds us that the world extends far beyond the narrow band of conditions we personally inhabit. Light enters the ocean, weakens, and eventually stops. Darkness remains. It has always remained. It will continue to remain stable and neutral, indifferent to the surface, patient beyond measure. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.